Hi KCET 2025 aspirants. So I hope all of you are preparing really well for your KCET examination, right? We have very few days left, so please work hard. And today in this video we are going to discuss the one shot of one of the very important topic from PU1 syllabus, and that is chemical bonding. Okay, so I'll be telling you what all things you need to focus so that this one video is enough for your complete chemical bonding revision. Okay, and I will also be including here previous year questions. So let us see here the first thing what all things we are going to study in today's video. So the first thing I have here is Lewis structure. This is very important question. Then we have ionic bond parameters. Then I have here valence bond theory, hybridization, Vesper theory, MOT, and hydrogen bonding. MOT stands for molecular orbital theory. Now starting from the weightage, so this chapter you can see has a lot of weightage from 2017 to 2024. Almost 1 to 2 questions have been asked every year. Okay, and this year the weightage is more. You can expect 2 to 3 questions from this particular chapter. Now coming to the first topic, that is Lewis structure. Okay, so under Lewis structure, just a minute. Okay, so under Lewis structure, the first thing that I want to discuss is why do atoms form bond, or why do different elements form bond. So it was observed that, or Lewis said that, different elements formed bond to become more stable or to gain a stable octet configuration. Now what is octet configuration? To have 8 electrons in the valence shell. Okay, that is your octet configuration. So Lewis said that every element tries to form bond to get this stable octet configuration in their valence shell. Okay, now and Lewis said that how do we represent Lewis symbol? We write the element and the valence electrons in the outermost shell. Okay, sorry, we represent the valence electrons in the form of dots. Like for example, if you see nitrogen atomic number is 7, its electronic configuration is 1s2, 2s2, 2p, 5. So how much valence, sorry, 2s2, 2p3, sorry, it is 2p3. So now if you see the total nitrogen valence electrons are 5, so it is denoted like this: 1, 2, 3, 4 and 5. This is the Lewis symbol for nitrogen. I hope this is clear. Next, what we are going to discuss, octet rule. So I have already told you what is octet rule. Octet rule says that atoms can combine either by transfer of valence electrons from one atom to another or by sharing of electrons in order to have an octet in their valence shell. So in the last shell, so when we have an atom X, there are different orbitals, right? So in the last shell, every atom wants to have 8 electrons. Now why is this? Because our noble gases, okay, if I see, our noble gases have 8 electrons in their valence shell. Okay, 8 electrons in their valence shell. So and we know that noble gas are very stable. So all the atoms think that if I also have 8 electrons in my valence shell, then I will be also very stable. And in nature, in an universe, every element, everything wants to get a stable condition. So that is why atoms try different methods, that is they form bond by different methods to get 8 electrons in the valence shell. Okay. Now what is covalent bond? So when 2 atoms share one electron pair, they are said to be joined by a single covalent bond. So for every bond we require 2 electrons. Okay, now if that 2 electrons, suppose a bond is there between A and B, and there is a bond between A and B, A donates 1 electron, B donates 1 electron, and now these 2 electrons belong to both of them. That is called as your covalent bond. Okay, now if there is one bond between A and B, then it is called single covalent bond. Okay, you can see example here. Suppose chlorine and chlorine. Now see, chlorine has 7 valence electron, this chlorine has 7 valence electron. So what they did, this donated 1 electron, this donated 1 electron, and they shared one pair of electron. Now you see this chlorine 1, 2, 3, 4, 5, 6, 7, 8. It also has 8 electron, it also has 8 electron. So now both of them has obtained their octet and they are stable. Similarly, if you see the example of CCl4, right? Carbon has 4 valence electron and it share 1 electron with each of the chlorine. So now chlorine also gets 8 electron, carbon also get 8 electron, their octet is satisfied. So these are your types of covalent bond. Now we will see next thing, that when two atoms share 2 pair of electrons, they are said to be joined by a double covalent bond. So it is not that always between two atoms there can be only one bond. It is not like that. Between two atoms there can be more than one bond also. So if between two atoms we have 2 bonds and these 2 bonds are formed by covalent by sharing of electrons, then we call it a double bond. You can see the example of carbon dioxide. Okay, you can see between C and O there are 2 bonds. Okay, now if I see when 2 atoms share 3 pairs of electrons, we call it as a triple bond. Okay, example is your nitrogen, where you can see between 2N there are 3 bonds, and if you see ethyne molecule between 2 carbon there are 3 bonds. Okay, so this is what is your covalent bond. Now what is your Lewis representation of simple molecules? So how can we represent simple molecules using Lewis symbols? Okay, so here are some rules. First is count the total number of valence electrons. So in an atom, what is the total number of valence electron, that you have to first calculate. Next, for anions add electrons and for cations subtract electrons from the valence electrons. Suppose a molecule is given, in that you have some negative charge, so that many negative charge you have to add to the valence electron. If in the compound there is some positive charge, then that much charge you have to subtract from the total number of valence electrons. Next, draw the skeletal structure, least electronegative atom at the center. In skeleton structure, you have to place the different atoms and the least electronegative atom should be at the center. Okay, now after accounting for the shared pair of electrons for single bond, the remaining electron pairs are either utilized for multiple bond or remain as lone pair. So now this I can better explain with an example. Okay, so let us try to draw the example of CO. Okay, so carbon has how many valence electron? Carbon has 4 valence electron. Oxygen has 6 valence electrons, so I have total 10 valence electron. This is a neutral molecule, there is no negative charge, no positive charge, so total valence electron remains 10. So now I will write CO and I have to arrange this 10 electrons so that both of them octet will be satisfied. Okay, so first I can do like this, one single bond I will use, 1, 2. Okay, next suppose I have 1, 2, 3, 4, 5, 6, and here it was carbon was having 4 valence electron, right? So I can form one more 3 bonds I can form between them, right? So I will draw a structure like this. So okay, so 1, 2, 3, 4, 5, 6 electrons are already used. Now but octet is not satisfied. Here the 6 valence electrons are there, here also 6 valence electrons are there. So I have total 4 electrons left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, total 10 electrons are used. In place of carbon, if you see 1, 2, 3, 4, 5, 6, 7, 8, its octet is satisfied. 1, 2, 3, 4, 5, 6, 7, 8, its octet is also satisfied. Okay, next coming to NO2 minus. Nitrogen has 5 valence electron, 6 plus 6 plus 1. So 6 plus 1, 7, 7 plus 5, 12 plus 6, 18. Okay, so I have total 18 valence electron. Now to arrange this one, I can just write first all the atoms. Okay, next I can 1, 2, 3, 4. I'm just writing to try to arrange this all elements. So 1, 2, 3, 4, 5, 6. Okay, nitrogen can have a lone pair here. Okay, so nitrogen 1, 2, 3, 4, 5, 6, 7, 8. Its octet is satisfied. Now 1, 2, 3, 4, 5, 6, 7, 8, and here 1, 2, 3, 4 and 5, 6. So have we used 18 electrons? So see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So total I have used 18 electrons and I have satisfied all the octet for all the atoms. So that is how you can do the Lewis structures. Okay. Next, coming to formal charge. So formal charge is something, the charge that a atom has when it is in a molecule. Okay, so molecule itself has a overall charge, but if a particular atom, what is that particular atom charge in when it is present inside a molecule, that is called as your formal charge. Okay, and how do we calculate the formal charge? Total number of valence electron minus bonding non-bonding electron minus bonding electrons by 2. Okay, I'll write the formula once again. So formal charge is equal to just a minute. Yes, so formal charge is equal to total valence electron, okay, minus non-bonding electrons. Non-bonding electrons means then I have minus bonding electrons. Okay, so now let us take an example. Suppose I have a charged oxygen molecule like this. Okay, this is the structure. So if I see O3, ozone, right? So how many electrons are there? So 6 3s are 18 electrons are there. So I have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 and 18. I want to calculate the formal charge of each of them. Okay, so here it is, 2 lone pairs are there. Let me a little broad, I can highlight it. Okay, I have here. Okay, so now we will calculate the formal charge of each of this oxygen. So this is O1, O2 and O3. Now if I see O1, okay, total valence electrons is how much? Total valence electron is 6, right? Plus, sorry, minus non-bonding electrons, how much I have? 1 2 3 4 5 6. Non-bonding electrons is 6, minus bonding electrons. So these are the bonding electrons. So I have bonding electrons by 2 you have to do. Okay, so I have how many bonding electrons? 2 bonding electrons divided by 2. So I will get charge is minus 1. So here I can say this charge is minus 1. Now coming to O2. Okay, so O2, if you see, I have here 1 2 3 4 5 6 valence electron of oxygen. Now non-bonding electrons are 2 and bonding electrons 1 2 3 4 5 6. 6 by 2 is 3. Okay, so I will get O2 here charge is plus 1. Okay, this one is plus 1. Next I have O3. Okay, so O3 is here 8. Total valence electron is 8 minus non-bonding electron 1 2 3 4. Okay, now bonding electron is 1 2 3 4. 4 by 2 is 2. 1 second. Yes, right. So here if I see, 1 second, okay, this I made a mistake. Valence, okay, I just erased everything, sorry. Let me just do it once again. So what is the formal charge formula? Valence electron minus non-bonding electrons, okay, minus bonding electron by 2. Okay, so I have already calculated the other two, so I will just do this one which was left. Here I have already got minus 1 and this was plus 1. For this oxygen I want to calculate, so it is total valence electron is 6 and here non-bonding electrons are 4 and bonding electrons are 1 2 3 4 by 2 and that is equal to 0. So the total formal charge of this oxygen will be 0. Okay, next, what are the limitations of octet rule? So there are certain elements whose octet rule is not satisfied. Okay, so we have odd, the incomplete octet of the central metal atom. So for example, if you see the molecule BCl3, okay, so here if I see the boron has 6 electrons only, right? So there are certain molecules whose octet are not satisfied but still they are forming bonds. Next, odd electron molecules. Okay, there are certain molecules where you find just 1 electron left, it is not left in pairs. Third one, okay, this is same. Third one does not explain about the shape and stability of the molecule. Okay, it doesn't explain anything about the shape of the molecule. And one more thing, here I have 6 electron and there are certain molecules like SF6 also. Okay, if you see F6. So there are 6 bonds and each is having 2 electrons, so it is 12 electrons, which is more than octet. So there are certain elements where the octet is not satisfied, it is less than 8, and there are certain elements where the octet is satisfied, octet is not satisfied because it is more than 8. Okay, so these are the limitations of octet rule. Now coming to something called as ionic bond. All of you might be knowing ionic bond is formed when one element loses electron completely and the other electron gains the electron, right, or other atom gains the electron. The one which loses the electron is called as cation and the one which gains the electron is called as anion. Now this cation and anion forms a bond like this. This is not actually a bond. So when you see they are opposite charges, so there is a force of attraction between them called as electrostatic force of attraction. Okay, clear? So this is your ionic bonds. Okay, so now ionic bonds is formed more easily between the elements with comparatively low ionization enthalpy and comparatively high negative electron gain enthalpy. Okay, so A plus should have, the one which is losing electron should have low ionization enthalpy and this one should have high electron gain enthalpy. Okay, next, lattice enthalpy. So what is lattice enthalpy? So lattice enthalpy is the energy required to break one ionic solid into its constituent gaseous ions. Like for example, if I have NaCl, okay, then the energy required to break it into its constituent gaseous ions, okay, this energy is called as your lattice energy. Okay. Next, we'll come to some bond parameters. So what is bond length? Bond length, if you know, the distance between the two atoms. Okay, suppose we have the these are the two molecules, right? The distance between the nucleus of the two atoms is called as your bond length. So we'll quickly discuss, not very important. Bond angle, suppose I have a bond here like this, A, B and A. So this angle is called as your bond angle. Okay. Next, so for example in water the bond angle is 104.5 degree. Okay. Next, bond enthalpy, this is important term. So bond enthalpy is the amount of energy required to break one bond. Okay, how much energy you have to give to break a bond, that is called as your bond enthalpy and its unit is in kilojoule per mole. Okay, that is defined as the amount of energy required to break 1 mole of bond of a particular type between two atoms in a gaseous state. Okay, so when the molecule is in the gaseous state, how much energy is required to break that bond, that is your bond enthalpy. Next, here one very important term is there. So if bond enthalpy means if you require more energy, so see, if bond enthalpy, okay, is very high, okay, that means what? The bond is very strong, bond strength is high. Okay, if bond strength is high, that equals to bond order, which I will show just now. Bond order is high, and if bond order is high, that is equal to bond length is less. So what exactly I want to say? Bond enthalpy, okay, is proportional to bond strength, is proportional to bond order, is inversely proportional to bond length. So if bond enthalpy is more, bond strength will be more, bond order will be more and bond length will be less. Okay. Next, bond order. So bond order exactly tells you between two atoms how many bonds are present, right? So number of bonds between two atoms in a molecule. Now isoelectronic molecules and ions have identical bond orders, for example F2 and O2 2-. So if you see F2 is having total electrons here, fluorine is having 18 electron, oxygen is also having 18 electrons, so they will have the same bond order 1. N2, CO and NO plus have same isoelectronic species, so their bond order will be same. Okay. Now with the increase in bond order, the bond enthalpy increases and bond length decreases. This is what I just explained you, the relation. Okay. Next parameter is your resonance. So resonance is what? When you have, see, Whenever a single Lewis structure cannot describe a molecule accurately, a few structures can similar energy positions of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of the hybrid molecule, and they describe the molecule accurately. Energy of resonance hybrid is less than the canonical structures. Now see here, suppose you see benzene structure. This is the structure of benzene. You can also have the structure of benzene like this. Right, so both the structures define benzene, but none of them can define completely. So we have a structure which is the resonance hybrid, means which is the mixture of these two, and it is denoted by like this. So these are your canonical structures, and this one is your resonating structures, sorry, resonance hybrid, right? So now it is always seen that the energy of the resonance hybrid will be less than the canonical structures. So we have some examples here. Okay, just a minute, I can show you. You can see there is one possible structure of O3, there is another possible structure of O3. Combination of these two, the resonating structure is given like this. Okay, so here is the next example, CO3 2 minus. So the structure you remember, CO3 2 minus, this is one structure. I have another structure like this, and I can have another structure like this, right? These all are the canonical structures for CO3 2 minus, and that is why the combined structure that I can write is this one. Okay, now similarly if you see for carbon dioxide, this is one structure. I can have a structure like this. Just a minute, yes. Oh, sorry, one second. Okay, so here I have lone pair, so this can be donated here, this can be shifted here, so I can get a structure like this as well. Okay, so these are the different structures of carbon dioxide. So similarly many resonating structures can exist. Next we have polarity of a bond. So what is polarity of a bond? So no bond of a compound is either completely covalent or completely ionic. Okay, so ionic nature in covalent bond is due to polarization. So ionic in covalent bonds are also some ionic properties are there due to the polarization nature. Now you can see here, if you see HCl, okay, so we think that this is a covalent bond, sharing of electrons takes place, but your chlorine is more electronegative, so there is a small charge developed in minus and plus, and that is why we can say that it is partly or it has some ionic nature as well as. Okay, now we have something called Fazan's rule, which tells you about the covalent character, that tells about the partial covalent character. Okay, so you can see yes, how to decide which. So it tells you about the partial covalent character in an ionic bond. So in an ionic bond, how much covalent character is present, because I said you no bond is completely covalent or completely ionic. So if one ionic bond is present, then how much covalent character is there in that ionic bond, that is given by Fazan's rule. So for Fazan's rule, the rules are: the cation should be smaller in size, and larger the size of the anion, greater is the covalent character of the ionic bond. Suppose I have an ionic bond in which cation is very small and anion is very large, then that is it has a much larger covalent nature. Okay, and one more thing, if the charge of the cation is more, greater is the covalent character of the ionic bond. So if charge on the cation is more, then also covalent nature is more. Okay, now for cations of same size, so if I have all the same size cations and charge, the one with the electronic configuration n-1 d and ns0 is more polarizing than the one with a noble gas configuration ns2 np6, typically of alkaline and alkaline earth metals. So if we have cations of the same type and one cation is there from D block and one cation is there from P block, then obviously D orbital will be, or D elements will be more polarizing. Okay. Next, the polarizing power of the cation, the polarizability of the anion and the extent of distortion of the anion are the factors which determine the percent covalent character of an ionic bond. So what all factors we have? Size of the cation should be small, size of the anion should be big, charge of the cation should be very high. Okay, so that will contribute to more covalent nature in an ionic bond. Okay, next, okay, we'll do some question practice here. Formal charge on the central atom of the ozone is, so we have already discussed ozone central atom. I'll do once more. Okay. So if I see the formal charge of oxygen, total there are 6 valence electrons, lone pairs of electron are 2, and here we have minus 1, 2, 3, 4, 5, 6, right, 6 by 2. So if I see here, this is plus 1. So the central atom charge is plus 1, option number C. Next, which of the following poses a net dipole moment? So if you see the structures, BF3 structure is like this. Okay, so the net dipole moment here moves this side and this dipole moment moves this side and cancels out each other. BeCl2 structure, if you see here also it is like this, net dipole moment is 0. Carbon dioxide structure, if you see, again the net dipole moment is 0. But if I show you SO2 structure, it is like this. Here what happens? The net dipole moment is there and it is not a complete 0 dipole moment. So option number A is the correct answer here. Next, which of the following pairs contains 2 lone pairs of electrons on the central atom? 2 lone pairs should be there. Okay, now what all structures I have? I3 plus, then I have H2O, okay, then I have NF3, I have XeF4, and then I have NH3, I have SO4 2 minus, and I have H2S. So let us see all the structures so that we will also have an understanding how to find out the number of lone pairs and bond pairs in an atom. So if I have I3 plus, so the structure you can see iodine, okay, iodine has 7 valence electron, okay, plus means 1 is lost, so total 6 valence electrons are there. Now out of this 6 valence electron, so I will draw like this 1, 2, 3, 4, 5 and 6. So here there is one more I where the bond is formed and here there is one more I where the bond is formed. So you can see that in this the central atom has 2 lone pairs. Now if you see water, oxygen has 6 valence electron, 1, 2, 3, 4, 5 and 6. So this one forms bond with hydrogen and this one forms bond with hydrogen. So again this one is also having 2 bond pairs on the central atom. So correct answer will be option number A. Next, HCl gas is covalent and NaCl is an ionic compound. This is because sodium is highly electropositive, hydrogen is a non-metal, HCl is a gas, electronegativity difference between H and Cl is less than 2.1. Okay, so whenever the electronegativity difference between two substances is less than 2.1, they form a covalent bond. Okay, so the correct answer here will be option number D. Next, here this is an example question, which of the following has the highest dipole moment? So if you see carbon dioxide, this is the structure, right? So here what happens? The net dipole moment becomes 0 because they are in opposite direction. If I see HI, this is the thing. In HI what happens? This is the dipole moment direction. There is some dipole moment definitely. Now if you talk about H2O, okay, so here we have lone pair, here we have lone pair. So now there is a dipole moment towards oxygen, there is a dipole moment towards oxygen, and these lone pairs also have a dipole moment, okay, towards the lone pair. So these two dipole moment have a net dipole moment in this direction. So there is a very strong dipole moment, net dipole moment is present in water molecule. If I see SO2, okay, so these dipole moments are in this direction because oxygen is more electronegative, and because of lone pair there is one dipole moment in this side. So here you see the dipole moments are in opposite directions, right? So there is a net dipole moment on this side and there is a dipole moment on this side, which will cancel the net dipole moment, or which will reduce the value. So that is why the maximum, here you see all are having in one direction, so that is why the maximum dipole moment will be in option number C. Next, in PO4 3-, the formal charge on the oxygen atom of PO is, okay, so just a minute, okay, fine. Okay, so if you see PO4 3-, the structure is like this. Okay, so you can see by structure the charge here, or the formal charge here is 0, here it is -1, -1, -1. Now the average value, because it is asking for PO bond, so you have to calculate the average value. So the total charge here is -3 and total number of oxygen is 4, right? So you have to do -3/4 and that will give you -0.75, that is option number C. Okay. Next we will move to our next concept, that is valence bond theory. Okay, you don't have to go too much in detail about valence bond theory, but what is the concept of valence bond theory? So valence bond theory says that the valence orbitals, means the last orbitals of an atom, participate in the bond formation. Okay, so suppose A and B are forming bond, then the last orbital of A and the last orbital of B will overlap and a bond formation will take place. Okay, that is the theory of valence bond orbital theory. You can see here, when two atoms come closer to each other, partial merging of atomic orbitals takes place, and this is called as overlapping of atomic orbitals, which results in the pairing of electrons. Okay, so suppose I have one atom A here, okay, and I have one atom B here. This has a valence orbital, this has a valence orbital, this has one electron and this has one electron. So the atomic orbitals, the valence orbitals overlap and their electrons are paired up to form a bond. Okay. Next, the extent of overlap decides the strength of a covalent bond. So more is the overlapping, stronger is the bond. Now in general, greater the overlap, stronger is the bond formed. Okay. Now therefore, according to the orbital overlap concept, the formation of a covalent bond between two atoms result by pairing of electrons present in the valence shell having opposite spins. Okay, so this is not important. Yes. Now talking about overlapping of atomic orbitals, right? So you can see here some diagrams where I am showing the overlapping of atomic orbital. So here you can see PZ orbital, okay, taken along the Z axis. There is a very good overlapping between PZ, PZ, okay. So when we have positive overlapping on each other, that is called positive overlap, and if you have positive and negative, that is called as negative or out of phase overlap. Now similarly, PZ and S can have a good overlap. PZ and S, if you have minus and plus, that is a negative overlap. Now if you see PX and PX, okay, this is also, there is a overlapping here, and if you have minus plus in the opposite side, then we have this is a negative overlap. Similarly PY, and here also we have positive and negative overlapping. Okay. Now when there is zero overlap, means there are no possibilities of any overlap in between PX and S orbital, okay, or you can take PY and S orbital, there cannot be any overlapping here, and PX and PY cannot have any overlapping because their orbitals will not merge with each other, means this much overlapping will not work for a bond formation. We need to have more overlapping between the orbitals. Okay, so what I can say, what all overlappings are possible? I can have PZ, PZ, okay, I can have PZ and S, I have PX and PX, I can have PX and PY, sorry, PY and PY, sorry, one second, yes, PX, PX and PY, PY are possible overlap. So here you remember, these two overlap will give you sigma bond, these two overlapping will give you pi bond, because it is sidewise overlapping, this is head on overlapping. Now which is, so this is possible. Which is not possible? You have px py overlapping is not possible, pxs is not possible, pys is not possible. Okay, note down this one. Next we can see here the type of bond, that is sigma and pi bond. So in sigma bond what happens, there is head on overlapping, direct face to face overlapping is there. So we have, what type of bond can give me sigma bond? Just now I told you, we can have SS, SP and PZ, PZ. Okay, you can see all the three types of overlapping here that can give you sigma bond. Now in case of pi bond, what we have? We have px px, or you can have py py. Px px or py py overlapping will give you pi bond. Okay. Next, strength of a sigma bond and pi bond. So because in sigma bond there is direct head on collision, whereas in pi bond there is sidewise overlapping, so the sigma bond will be more stronger because there is greater extent of overlapping of the orbitals. Just now we studied, more is the overlapping, more is the extent of overlapping, better will be the, or stronger will be the bond. So in sigma bond, because there is direct head on overlapping, so you should remember that sigma bonds are more stronger than pi bonds. Okay, sigma bonds will be more stronger than pi bonds. Why? Because the extent of overlapping is smaller in pi bonds, whereas greater in sigma bonds. Okay. Next, hybridization. So what is hybridization? Hybridization is just little bit extension of valence bond theory. Okay, so valence bond theory was saying that the valence orbitals are there and they were directly forming bond with the atoms, right? Now hybridization says that the valence orbitals of an atom first undergoes a mixing, they form hybrid orbitals. Now these hybrid orbitals overlap with the orbitals of other element. Okay, now for example, you can see, for example, I will give you a small example. Suppose I have CH4. Okay, so what is the valency or electronic configuration of carbon? 1s2, 2s2, 2p2, right? So here what happens, I have 2s2, I can denote like this, and I have 2p2. So what, see, for forming 4 bonds I need 4 unpaired electrons, right? But there are only 2 unpaired electrons, so there will be one excitation here and it will be 1s, 2s and 2p3. So it is like this. Okay. Now if valence bond theory we will observe, it will tell that okay, 2s will form bond, 2p will form bond, the bond formation will take place like this with hydrogen atom. But what does hybridization says? That this s and p3 orbitals will first combine or will first undergo a mixing. So if it undergoes a mixing, so there is 1s and 3p orbitals, so they will mix with each other, and now we will get 4 atomic orbitals are combining, so we will get now 4 new orbitals, right? We got now 4 new orbitals, each of them is called as sp3. Okay, so there is no s, there is no p now, all of them are sp3 hybrid orbitals. Okay, so now these, so now carbon has what? Carbon has no more like this valence electron, it has 4 sp3 hybrid orbitals which will form bond with hydrogen. Okay, so these are what? These are your hybrid sp3 orbitals of carbon. So that is the meaning of hybridization. Before forming bond, there is intermixing of atomic orbitals to give you new hybrid orbitals. Okay, so let's see here. Okay. Now first of all, you should be knowing that number of hybrid orbitals is equal to the number of orbitals that get hybridized. So I just showed you now 1s and 3p. So there are a total 4 atomic orbitals involved. So these 4 atomic orbitals will mix to give you 4 new hybrid orbitals. Okay, this is the first thing. Next, they should be equivalent in shape and energy. So those atomic orbitals which are undergoing mixing should be having equal or similar energy and shape. Okay, next thing, Next thing, directed in space to reduce the repulsions and can indicate the geometry of the molecule. So hybridization can be used to predict the geometry of the molecule, which is given by your Vesper theory. Okay. Now if I show you what are the types of hybridization, first hybridization we have is sp hybridization. Here the shape is linear, bond angle is 180 degree, and examples are your BeCl2 or C2H2. So you can see here beryllium are having this sp hybrid orbital. This is the hybrid orbitals of beryllium, and yes, beryllium hybrid orbitals are here and it is forming bond with p orbitals of chlorine. Okay. Similarly, if you see ethyne, so ethyne has one, it is having one hybrid orbital, this is having one hybrid orbital, they are forming a sigma bond, and these are your unhybrid orbital. The red one is your hybrid orbital which is forming bond with carbon carbon, and we have one with hydrogen. Okay. Next you have sp2 hybridization, trigonal planar, bond angle is 120 degree. You can see example here BCl3 and we have C2H4. Okay. So here also you can see the orbitals of boron undergoes hybridization to give you 3 sp2 hybrid orbitals which can form bond with the p orbitals of chlorine. Similarly, here each of the carbon forms 3 hybrid orbitals, right? So 3 carbon, and remember these hybrid orbitals will always form sigma bond. So I just want to explain for this one so that it will be clear. C2H4. Okay. So carbon, what is the electronic configuration? 1s2, 2s2, 2p2, right? So here I have like this. Okay. If I just see the structure of C2H4, it is like this. So this carbon is forming 3 sigma bond, so it requires 3 empty orbital. Okay. So or 3 unpaired electrons should be there. So what will happen now? This one will get excited and will form an excited state like this, and these 3 orbitals 1s and 2p will form hybrid orbital to give you 3 new hybrid orbitals. Okay. These all are what? sp2 orbitals. Okay. There is one p orbital which is unhybridized. Now if I show you carbon and carbon, each of the carbon has 3 sp2 hybrid orbitals. So I have one sp2 hybrid orbitals like this, one sp2 hybrid orbital like this, and one like this. Okay. Similarly, this carbon is also having like this. Just a minute. Yes. So this is also having hybrid orbitals. Now, so one sigma bond is formed here between carbon carbon, another sigma bond is formed between hydrogen and carbon, right? Now you see each of the carbon also has one unhybridized orbital, right? So for unhybridized orbital we show with 2 same lobes. Now these 2 undergo pi bond formation. Okay. So that is what is your molecule symbol, how it is denoted. Similarly, for sp3 hybrid orbital you have tetrahedral shape, bond angle is 109 degree, and example is CH4, C2H6, H2O and H3. Okay. Fine. Now moving towards, you can see other examples as well. Now coming to hybridization which includes d orbital. Okay. So just now we see s and p orbital, right? sp, sp2 and sp3. Then let us see some hybridization where d orbitals are also involved. So first we have is dsp2. Here the shape you should remember, it is a square planar shape, and in this we have one d orbital, one s orbital and 2 p orbital. Examples here you have NiCN4 2 minus, PtCl4 2 minus. In coordination chemistry you must have been known about this particular hybridization. Next, trigonal just a minute, yes. Next we have trigonal bipyramidal sp3d hybridization. Here you have 1s, 3p and 1d orbital, and here you have pf5 and pcl5 as an example. Next, for square pyramidal you have sp3d2 hybridization. Okay. Here you have 1s, 3p and 2d, example is brf5, and the same octahedral also has sp3d2 hybridization and d2 sp3 hybridization, both are possible. and here also we can see the examples. Okay, so please remember this table with the examples. Now we will move to hybridization. So hybridization involving d orbitals. So yes, one second. Okay, so we can clearly see phosphorus has 5 valence electron, right? So you can see the electronic configuration of phosphorus is 3s2 3p3, right? So what happens here? So if I see the electronic configuration of phosphorus is like this: 3s2 and 3p3, right? So here phosphorus has to PCl5, phosphorus has to form 5 bonds, right? So we need 5 unpaired electrons. So it is 3s, this one is 3p. Now one electron gets excited here. Okay, so 3s, 3p and 3d. So we have 3s, then I have 3p and then I have 3d. Yeah, like this one. Okay, so you can see 3s, 3p and then I have one 3d, and these orbitals undergo hybridization. So there is sp3d, right? So these 5 orbitals form 5 hybrid orbitals, that is sp3d hybrid orbitals. Okay, 5 new hybrid orbitals are formed. Now these hybrid orbitals of phosphorus, you can see here there are 3 orbitals in one plane and 5 orbitals in the other plane, and they are forming bond with chlorine molecules. Okay, similarly you can see for SF6 sulfur, if you see electronic configuration, it is 3s2 and 3p4, right? I need 6 unpaired electrons. So the configuration is like this. Okay, so I need 3 unpaired electrons. So I have to, what I have to do, I have to excite them, right? So I have 3s, then I have 3p and then I have 3d. Okay, so 1 like this. Okay, now these orbitals undergo hybridization, that is sp3d2, to form 6 hybrid orbitals, and then they overlap to give you the molecule. Okay, next, Vesper theory. So Vesper theory tells you that the atoms, okay, Vesper theory tells you that the bond pairs and lone pairs arrange themselves in such a way that the repulsion is minimized. Okay, and the lone repulsion order is what? Lone pair, then lone pair, and then bond pair. Okay, so you can see here, if the total number of electron pairs is 2, then we get a shape that is linear. Example you should be knowing. If the total number of electron pairs is 3, then you get a trigonal planar shape BF3. Total electron pairs are 4, then it is tetrahedral. So I will also be mentioning the hybridization here. This is sp, sp2, sp3. Okay, if 5, then it is sp3d, trigonal bipyramidal. Example you should remember, sp3d2, then it is octahedral. Okay, next, if there is lone pairs are also involved. Okay, so if the total number of electron pair is 3, okay, in that 2 bond pairs and 1 lone pair is present. Total number of electron pair is 3, in that 2 are bond pair and 1 is lone pair. Okay, in that case the shape of the molecule will be bent. What is the geometry? If you remember, for 3 the shape is, so geometry is trigonal planar. This is geometry. Okay, when you talk about the shape, you don't consider the lone pair, you only consider the bond pair. So if I just consider this bond pair, this is a bent molecule, right? Example is your SO O3 and SO minus. Sorry, what is this? O3, you can write down the example. Okay, and here what is the hybridization? 3 electron pairs are there, so it is sp2. Okay, next, if I see that there are total 4 bond pairs. Okay, so I have total, electron pairs are 4, that means hybridization is sp3 and geometry is tetrahedral. Out of this 4 electron pair, if 3 are your bond pair and one lone pair. Okay, so you just have to ignore this one. Then the shape will be trigonal pyramidal. Example is NH3. Now similarly, if I have two bond pairs and two lone pair, out of this two are bond pair and two are lone pair, then you have to ignore this. This is a bent molecule. Example is water. Now if I see total bond electron pair is suppose 5. Okay, and in that we have 4 bond pairs and 1 lone pair. So if I have 4 bond pairs and 1 lone pair, then it is a seashore shape and it is called SF4. And next, if I have 3 bond pairs and 2 lone pairs, 3 bond pairs and 2 lone pairs, then that is called T shape, and example here is ClF3. Okay, next, if I have electron pairs as 6, okay, and I have 5 bond pair and 1 lone pair, we have 5 bond pair and 1 lone pair, then it is square pyramidal BrF5. Okay, and if you see the same 4 bond pairs and 2 lone pairs, then you have to ignore this 2 and only 4 bonds are there in one planar, it is square planar. Example is XeF4. Yes, so now we will do some questions here. The percentage of S character in the hybrid orbitals of nitrogen in NO2 plus, NO3 minus and NH4 plus. So first of all, you should be knowing the hybridization in each of them. So very easy one is your NH4 plus. So if you see NH4 plus structure is like this. Okay, so nitrogen is forming 4 sigma bonds and there is no lone pair, so this hybridization is sp3, and in sp3 the S percentage is 25. So the last one will be 25, so I have 2 options with that, I can eliminate the other 2. Now NO3 minus, if you see NO3 minus, NO3 minus, okay, here also, here nitrogen has 3 sigma bonds, that means sp2 hybridization, so S character is almost 33.33%. So the second one has to be 33.33%, so option number B here. Okay, next, the bond angle in pH4 plus is more than that of pH3. So if you see the structure of both, pH4 plus is like this, okay, and this is pH3. Okay, here also hybridization is sp3, here also the hybridization is sp3, here the geometry and shape is tetrahedral, here it is pyramidal. So now what happens, the bond angle in sp3 hybridization is 109 degree 0.28 minutes, right? But here also what happens, due to this lone pair, there is lone pair and bond pair repulsion. Due to this repulsion, what happens, the hydrogen comes closer to each other and the bond angle decreases. So what I can say, due to the lone pair bond pair repulsion in pH3, the bond angle here is less than this one. Okay, next, the state of hybrid orbitals of the carbon. So if I see CO2, right, so I have 2 sigma bonds. 2 sigma bonds means it is sp hybridization, right? Sp hybridization, I have only one with the first option, so option number C. CH4 sp3, CO3 2 minus is sp2. Okay, next, the hybridization of carbon in diamond, graphite and ethyne molecule. So if I know ethyne molecule, it is like this, right, and here I have each carbon has 2 sigma bonds, so that means the hybridization here is sp. I can eliminate these 2. Now in carbon in diamond has an sp3 hybridization, okay, sp3 hybridization, here it is given sp2, so option number B, and in graphite it is sp2 hybridization. Next, the pair of compounds having identical shapes for their molecule. So if you remember, I have just done so many examples. CH4, so I will write for all, so we can have a practice as well. CH4 is tetrahedral, hybridization is sp3. SF4, if you remember, it is a seesaw shape and hybridization is sp3d. Next I have, this is BeCl2 actually. In BeCl2 the shape is linear, okay, and hybridization is sp. ClF2, so if I have ClF2. Okay, sorry, this is again ClF3, not ClF2, ClF3. Okay, so if ClF3 is there, then it is ClF3, right? So this is also sp3d hybridization and shape is T shape. Okay, yes. So there are actually 7 electrons, 3 are used. Chlorine has 7 electrons, right? So out of 7, 3 is used, now 4 are left. Yes, this is a T-shaped molecule and the hybridization is sp3d. Next, okay, so till now we haven't got the answer. We want same shape, XeF2. So okay, XeF2, if I see XeF2, it is having if you see, Xe has 8 valence electron, out of that 2 is forming bond, and I have 4 lone pairs, right? So 1 2 3 4 1 2 3 4 5 6 1 2 3 4 5 6, and I have one more like this, right? So this is also, this is a linear shape. Okay, and hybridization 1 2 3 4 5, that is again sp3d. Okay, so this is linear, and if you see ZnCl2, it is also like this, and this is also a linear molecule, so option number C. Okay, now SO2, if you see, it is a bent molecule and CO2 is a linear molecule. Clear? Next question, which one of the following species has tetrahedral geometry? So for tetrahedral geometry, if you see, we can see BH4 minus. So boron has 4 electrons here, right? Generally it has 3 electrons, but with this charge it has 4 electrons and it forms 4 sigma bonds. So the hybridization here is sp3. Okay, and that is why it is a tetrahedral geometry. Next we will see about MOT and hydrogen bonding. Okay, so first of all, what does MOT tells you? See, in MOT what happens, the electrons in a molecule are present in various molecular orbitals. How the electrons in an atom are present in an atomic orbitals, the electrons in a molecule are present in molecular orbitals. Okay, now the atomic orbitals of comparable energy and proper symmetry combine to give you molecular orbitals. Now when the hybridization happens, just imagine, in hybridization what happens, the atomic orbitals of the same atom, means suppose I am having atom A, then the atomic orbitals of atom A combine to give you hybrid orbitals. In case of molecular orbitals, what happens, the atomic orbitals of A and B will combine. The atomic orbital of A and B will combine to give you molecular orbitals. Okay. Next, the atomic orbitals of comparable energy and proper symmetry combine to form you molecular orbitals. So two types of molecular orbitals are formed. One is bonding molecular orbital, which is having lower energy, and the anti-bonding orbital, which is having the higher energy. Now this bonding molecular orbital is your positive overlap, okay, and this anti-bonding orbital is your negative overlap. Okay, you can, this one is called in phase and this is out of phase. Okay. Next, molecular orbitals are filled in accordance to the Auber principle, means lower orbitals or lower energy orbitals are filled first and then the higher energy orbitals. Okay. Next, so you can see, for example, you have one molecule A, you have one molecule B. This has one atomic orbital, this is having one atomic orbital. Both of them will combine to give you bonding molecular orbital. So this is your positive overlapping, this is your negative overlapping. Okay, so here we get sigma and here we denote it as sigma star. Okay, so the anti-bonding orbitals are shown with plus sign. Okay. Next, what are some conditions of molecular orbital theory? That the combining atomic orbitals must have the same energy or nearly same energy. Okay. Next, the combining atomic orbitals must have the same symmetry about the molecular axis. And then the combining must overlap to the maximum extent. Okay, the overlapping should take place very good to form your bonding and anti-bonding molecular orbitals. Okay. Next, what are the types of, okay, so types of bonds form, one is your sigma bond and another is your pi bond. So symmetrical around the bond axis and the pi bonds will be unsymmetrical around the bonding axis. I can show you like this here. So if you see, for example 2pz and 2pz is there, these two will combine to give you one sigma bond and one sigma star bond orbitals. Okay. Next, if you have 1s and 1s, they will also form sigma bond and sigma star bond. So whatever we have seen there, sigma bonds were formed by what? SS overlapping, SPZ overlapping, PZ overlapping. So if these atomic orbital of atom A and atom B are overlapping, then you will get sigma and sigma star, right? And on the other hand, if you are overlapping with px and px, means px of A and px of B, then you will get pi orbital and pi star orbital. Okay, px and py can combine you to give you pi and pi star orbital. Next, this is very important. You should remember the order, how we feel in Abwehr principle, right? First 1s, then 2s, then 2p, then 3s. Similarly, in molecular orbital theory also we have a order. Okay, so what is the order in case of this one? So you have to remember, for means up to 14 electrons there is a particular method is followed. So first we have sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. After that we have pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py and sigma star 2pz. Okay. Next, in case of O2 and F2, means more than N2, so what happens, there is a small exchange that takes place here. So after sigma star 2s we get sigma 2pz, and after that here pi comes. This exchange takes place in the orbitals greater than N2, that is O2 and F2. Okay. So here what is this molecular orbital theory can tell us? We can calculate the bond order. So bond order is equal to half of number of bonding electrons minus number of anti-bonding orbitals. And it can also tell you about the magnetic nature, whether it is paramagnetic or diamagnetic. Okay, so if there is paramagnetic or diamagnetic, so if there is unpaired electron, then it is paramagnetic. If no unpaired electron, then it is diamagnetic. Okay. Now here I want to tell you some trick to calculate bond order as well. So you have to calculate the total number of electrons in a molecule. If the total number of electrons comes out to be 14, okay, just a minute. Okay. If the total number of electrons is 14, then the bond order is 3. Okay. If it is 13, then it is 2.5. Sorry. Okay. 15, 16, 17 and 18. Remember this trick, it will be very much useful in your solving of questions. Many questions will be asked from here, you can easily do here. Okay, so if you know this, if the total number of electrons you can calculate, then bond order easily you can predict. Okay, otherwise you have to do this formula and do, which is very time consuming. Clear? Next, we'll see the bond order. For example, sigma, for example H2 molecule, right? So H2 molecule has only 2 electrons, so sigma 1s, the lower orbital is sigma 1s, sigma 1s2. So bond order, so if I draw the electronic configuration, the bond order, half of number of bonding electrons is 2, anti-bonding electrons is 0, so that is 1. Okay. And what is the magnetic nature? It is diamagnetic because there is no unpaired electrons. If you see He2, total 4 electrons, right? So sigma 1s and sigma star 1s. So if I see bond order, half of number of bonding orbitals minus anti-bonding orbitals, so it is 0, right? So bond order is 0 means the molecule does not exist. So you can see helium 2 does not exist. And what is the magnetic nature? No unpaired electron, again this is diamagnetic. Li2, if you see, Li2 is having 6 electrons, right? Hydrogen, helium, lithium, total 6 electrons. So I have sigma star, sigma 1s, sigma star, then sigma 2s2. So what is the bond order here? Half into bonding orbital is 2 plus 2, 4, anti-bonding is 2, so it is 1. Okay. And here also we have no unpaired electron, so it is diamagnetic. Okay. Next we have carbon molecule. Carbon molecule is having how many electrons? 6 plus 6, 12 electrons, right? So first sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px, pi 2py. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11, 12. What is the bond order? Half into bonding electrons minus anti-bonding. So bonding electrons are 1, 2, 3, 4, 5, 6, 7, 8. Okay, and anti-bonding are 1, 2, 3, 4. So 8 minus 4 is 4, 4 by 2 is 2. So carbon molecule has 2 bonds. Just let me check once, wait, 1, 2, 3, 4, 5, 6, 7, 8 and 1, 2, 3, 4. Okay, yes, so this is the molecule, and whether it is paramagnetic or diamagnetic, again diamagnetic because no unpaired electron. Next, oxygen, if you see, we saw that in oxygen there will be a change in the order. So first total we have 16 electrons, right? Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. After that pi 2pz will come, then pi 2px, pi 2py, pi star 1 and 1. Here when you are filling the electrons, you should fill one by one because they are in the same energy level. So here if I see the bond order, half into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons are there in the bonding minus. Anti-bonding 1, 2, 3, 4, 5 and 6. Again 2 I am getting here, right? So you know in oxygen there is two bonds are there. Next, if I see here the what I was saying, the paramagnetic nature. So you can see unpaired electron, so it is a paramagnetic in nature. Okay. Next, what is hydrogen bonding? So hydrogen bonding is formed when hydrogen is attached to one of the electronegative atom, right? Like N, oxygen or fluorine. Okay, and we have this any one of these atoms. Okay, so the lone pair of this one and this one can form a bond, okay, or can form an attraction. So hydrogen bond can be defined as the attractive force which binds hydrogen atom of one molecule with the electronegative atom of another molecule. Okay, so I should have one hydrogen which is attached to one electronegative atom. Okay, the bond should be formed between different electronegative atom of another molecule. Okay. Next, we have two types of hydrogen bonding, intramolecular and intermolecular. Intramolecular means between different molecules. Okay, so here this is a difference. Sorry, this is your intermolecular. Okay, this is intermolecular between molecules, and this is your intramolecular. Okay, means within the same molecule you are having hydrogen bonding. Okay. Now we'll do some questions here. Which of the following is an correct statement? Hydrogen bonding is stronger than dispersion force? Yes. Sigma bonds are stronger than pi bonds? Yes. Ionic bonding is non-directional? Yes. Sigma electrons are referred to as mobile electrons? No. Sigma electrons cannot move. Pi electrons can move during resonance, but sigma electrons are non-mobile electrons. Okay. Next, the correct order of boiling point of the compounds. So here we have strong hydrogen bonding. So water has a very strong or very high boiling point. So option number B. Arrange the following in the increasing order of their bond order. Okay, so I told you a trick to calculate the bond order. So if you see, so let me first draw that table: 10, 11, 13, 14, 15, 16, 17 and 18. So it is 3, here 2.5, 2, 1.5, 1, 2.5, 2, 1.5 and 1. Now 8 plus 8 is 16, right? So O2 bond order, 8 plus 8 16, it will be 2. O2 plus 8 plus 8 16 minus 1 15, this one will be 2.5. O2 minus 8 plus 8 16 plus 1 17, it will be 1.5. O2 2 minus 8 plus 8 16 17 18, that is 1. So bond order you have to arrange. So highest will be O2 plus. So I have only one option with that. So option number D. So first O2 plus, then I have O2, then I have O2 minus, then I have O2 2 minus. Okay. Next, So this is a question for you. Using MO2, compare O2 plus and O2 minus species and choose the correct option. O2 minus is less stable. Both O2 plus and O2 minus are paramagnetic. O2 plus have higher bond order than O2 minus. O2 plus is diamagnetic while O2 minus is paramagnetic. So this is a homework question. Try this and answer it in the comment section. So this is, you have to find the incorrect option here. Okay. So yes students, so this was a complete revision of chemical bonding. All the important concepts I have covered. Please practice these previous year questions and focus mostly on Vesper theory. Many questions will be asked from your Vesper theory. Okay. So if you have doubt in any of the concept, please comment down. I'll definitely address to it. And thank you for watching. And please remember, we are just left with few days and we have to study really hard at this point of time. So please do not waste even a single minute. Work really hard. And if you need any help, do tell me. Okay. That's all students, and see you soon in the next class. Do not forget to subscribe the channel because we are going to come up with so many informative videos for all of you. Thank you for watching.